Imagine you are on a TV show with three doors, one hiding a prize and the other two empty. You are asked to pick one, and then the host reveals an empty door and offers you the chance to switch. This puzzle, now known as the Monty Hall Problem, traces its roots back to the 1960s game show Let's Make a Deal, hosted by Monty Hall. Later, in 1975, it appeared in a letter to the editor of the American Statistician by Steve Selvin. But it became truly famous in 1990 when Marilyn's voice Savant, who was known for having one of the highest recorded IQ, answered the puzzle in her Ask Marilyn column in Parade magazine. Her solution sparked a huge controversy, as many PhDs and mathematicians from across the country insisted that she was wrong. At first glance, it feels like the chances are 50-50. After all, once Monty opens a door, there are just two left. But Bayes' theorem shows us that our intuition is misleading. So, in this video, I'll take you step by step. First, we will count all the wind possible scenarios to analyze the classical Monty Hall problem. Next, we generalize the problem to n doors. Using Bayes' theorem, we'll see that the probability of winning by switching is n-1 over n. Next, I'll show you a dynamic histogram so you can actually see how the probability of winning by switching grows as the number of doors increases. Finally, we'll look at a twist. What if Monty only reveals one door when there are n doors? The math takes a surprising turn. Before we dive in, just keep in mind that the host always knows where the prize is. And when he reveals a door, he randomly picks one of the empty doors that is different from the contestant's choice. This detail is crucial because it ensures that the odds shifts in a very specific way. Since Monty always knows where the prize is and only reveals empty door, the situation doesn't reset to 50-50 the way our intuition suggests. To see why, let's carefully count all the possibilities. Suppose you pick door 1. There are 3 possible prize locations: behind door 1, door 2, or door 3. If the prize is behind door 1, 1/3 chance, Monty can open either door 2 or door 3. Both are empty. And in this case, stay-in wins and switching loses. If the prize is behind door 2, 1/3 chance, Monty must open door 3, showing it to be empty. And switching to door 2 wins while staying loses. If the prize is behind door 3, 1/3 chance, Monty must open door 2, and again switching wins while staying loses. Repeat the same logic if the contestant had chosen door 2 or door 3 at the start, and the pattern is identical. In each case, there is a 1/3 chance that staying wins, but a 2/3 chance that switching wins. Counting across all 9 possible scenarios, switching gives 6 wins out of 9, while staying only gives 3 wins out of 9. That's why, in the classical Monty Hall problem, the probability of winning by switching is 2/3, while the probability of winning by staying is only 1/3. Now that we have seen how the classical Monty Hall problem works with 3 doors, let's extend this to a scenario with n doors. The key idea remains the same. Monty always knows where the prize is and will reveal all but one other door. Right at the start, every door is equally likely to hide the prize, so each door has a Fourier probability of 1 over n. We now examine what happens after the host, who knows where the prize is, and randomly opens n-2 empty doors different from your choice. For that, we define the event E, that's the host reveal -2 empty doors. Using Bayes' theorem, we compare superior and the posterior probabilities for the contestant selected door. Let's assume that the contestant pick the door number 1. The probability of door number 1 can seize the prize such that the event E is equal to the product of the probability of door number 1 to concede the prize and the probability such that door number 1 hide the prize over the probability of the event E. Because Monty always can reveal n-2 doors to be empty, regardless of whether the prize is behind your door or one of the others. The probability of the conditional term in the numerator and the denominator are equals to 1. And because the probability of door 1 to concede the card are equals to 1 over n, the posterior probability of the contestant chosen door remains 1 over n. Since the host leave one unopened door different from the contestant chosen door, by using the complementary of the event door 1 concedes the prize, the probability of switching is n-1 over n. Now that we have shown mathematically that staying always keeps its original probability of 1 over n and switching gives you n-1 over n, let's see what that looks like in practice. Here is a histogram plotting both probabilities as the number of doors increases, starting from 3 doors and going all the way up to 1500. Watch now the bar of staying, which begins at 1/3 when n equals 3, steadily shrinks closer and closer to 0 as the number of doors grows. At the same time, the bar for switching, which starts at 2/3 when n equals 3, rises higher and higher, approaching certainty. Now, let's see what happens if the host reveals only one empty door. Those probabilities on the screen still equals to 1. By Bayes' theorem, the probability that your original door has the price remains 1 over n. That means the probability that the price is behind one of the other doors is n-1 over n. Since there are now n-2 unopened doors left, and each of them is equally likely to hide the price, the probability for each of those doors is n-1 over n times n-2. And that completes our proof.